right, welcome back. So today I want to talk about correlation. So you've heard the term, you've probably had it in some physics class at some point, and I want to talk about how we parameterize that. So always go over, like, these are the books that you can use. So last week at the midterm, we did the line fits, we worked on visualizations, like all these things are now coming in our toolbox. And now we're getting to the next part of the toolbox, which is I have two sets of data. Are they correlated or not? I have two sets of data. Do they come out of the same parent sample, or are they distinct? So we do have a bunch of statistical tests for correlation: Pearson, Spearman, Kendall. Sample versus distribution. So you can actually test versus a distribution or test versus another sample. Sample versus sample. KS and AD test are for, I ran out of space, but that's the Kolmogorov-Smirnov test and the Anderson-Darling test. And then bootstrapping is what we'll work on next week, but it is something that you can do with these. So science questions are these two things related? Do they know about each other? That's a very basic scientific question, right? So does A know about B? Are these cases all from the same population? Critical test for anybody who wants to then compare two studies, for example. If I do a questionnaire, and I do this at St. Matthew's, and I do this at Western Library, for example, I am getting to very different sets of people coming through. So if I start comparing those two things, did I actually take that into account? So, and is this data consistent with this distribution? That's another one. Like, the theory says this should be log normal. The theory says that this should be a Gaussian distribution. The theory says that this is an exponential. How good does my data actually conform to that? So these are three questions that you need a statistical test for. I need to know how good and what's bad, and I need to then have a quality of how good my test is. Right, so remember the p-value, right? Odds that this was a random happenstance, the tails of the Gaussian distribution. The p-value is what we get from statistical tests. We get a measure of how much of these questions, and then how confident are we in that particular result. This depends on the sample size. This depends on the size of the effect. Yes? All right. Correlations. So we start with correlations. One goes with another. Correlation does not equal causation. I'm almost contractually obliged to say that immediately, because just because A and B go up together doesn't mean A causes B or B causes A. Right? Both of them can have a joint cause, or it can be something that is just happenstance. Shoe size and height, for example, are two things that are correlated simply because bigger people have bigger shoes, like bigger people have bigger clothes. These are things that have a common causation kind of thing. We are very much interested in finding correlations. If A does know about B, that tells us something. And so how to find them and how to quantify them is therefore critical in any big data set. And so any question is like, is the correlation linear or nonlinear? If I scale A, does B scale as much, or does it just go up, but it depends a little? It's like second order or third order. It's like as A squared, or A to the power 3, or as square root A, for example. So linear versus anything but linear is a second thing to look at. All right, we're in spooky season, so I have to say, like, inferring causation from correlation is a scary, scary thing, because you don't know if A causes B or B causes A. And if I want to really show off, I'll say the Latin phrase for that. So they've known about this for a while: post hoc ergo propter hoc. After, therefore, because of it. That's not always the case. Just because an event happened after it doesn't mean that event A caused event B. So, for example, I used to think correlation implied causation. Then I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe. OK, So you can have fun with that. There's a fantastic website called Spurious Correlations, where, for example, the number of people who drowned by falling into a pool and the number of films Nicolas Cage appeared in is very strongly correlated. As a function of over the year, here's the number of drownings, and on the y-axis we got the number of films Nicolas Cage is in, and on this one we have the number of drownings by people falling into pools.
Very concerning. Someone needs to take out Nicolas Cage.
Right, somebody should tackle the man and basically give him something else to do. Right, this is the kind of thing, this is extrapolate into absurdum, right? Go into where it's really clearly nuts. This is something this is helpful. It's like, look, this is a great correlation. The points follow each other, right? Here it goes up, and it goes back down, and here it goes up, and yeah, the number of Nicolas Cage movies went up. This doesn't even have a common cause, other than, I don't know, more people in California bought swimming pools because Nicolas Cage made them a lot of money. This is getting very tenuous.
Or watching a Nicolas Cage movie next to a pool and
it's terrible.
Surprised by Nicolas Cage's appearance and existence that they simply were just forced into the pool.
Look, it's no low number statistics, and it's simply, in a large enough database, you will find a correlation between A and B. You will find correlations. We'll get to that in a minute. My favorite version of this is with maps, because you can hang a story about it. You have predilections about, like, well, you know, these people in this part of England, you know, they don't do things or whatever. Here, for example, we have on the left the results from voting whether or not people wanted to leave the European Union or wanted to stay in the European Union. And then in 1992, we have the areas that were affected by mad cow disease and the ones that were not. And the correlation is amazing, right? The same counties have the same colors in both maps. Oh my gosh, this is a one-to-one correlation. Or, again, underlying effects are the yellow bits here are the heavily urban areas of England and Wales. And so, yes, you don't get mad cow disease in the middle of London because you don't have cows to begin with. The fact that I'm looking at here in both cases is urban versus rural and nothing else. My favorite things with maps is that 99% of the time when you put two maps together, especially when you bin it, understand that when you map something by county, you are by definition binning it. You're putting in, like, all the people that voted, Remain in the blue areas, for example, you've left those out. You've moved that detail out of your map. It's no longer there. So yes, correlation looks amazing after I've binned the data and put it on a map so that all the detail disappeared. And really what I'm looking at with maps often is like dense versus non-dense population, urban versus rural, that kind of thing. However, maps are not necessarily there's a reason we build maps. There's a reason we look at this. So this is the classical case. This is one of the first examples of looking for correlation and visualizing it. This is the cholera map in London. There was a big cholera outbreak, and these black dots are like essentially where the cases for patients were. Now this is a modern version of that. Here is where the cases are, and then I do I map out where the water stations, the pumps are for each neighborhood. And then what I do is, like, between this pump and this pump, the equal line is like, this is the equal distance between either pump. This is called a Voronoi map. And so if I go like, this is the line where if I'm standing on the line, it's the same distance to either pump. So if I live here, I probably go to this pump for my drinking water. And if I live here, I probably go to this pump for my drinking water. Remember, this is 19th century London. Not everybody has water being piped into their houses. That happened later. So you went to a well to get your drinking water. And so look at that. Cholera is basically all around the Broad Street well. That is a cause. You can think of, like, if your theory is, if your hypothesis is, a well is causing this. Drinking water is causing this, which is wasn't clear up until that point, right? People thought cholera came from bad food or bad air, or, well, they called it miasma. So it was like, oh yes, definitely don't wash yourself, like that kind of, like, it comes, you need to have your natural body odors, that kind of thing. Like, there was all kinds of nutty stuff out there, but nobody went out and tested it. So here's a hypothesis. It comes from the drinking water. Test, let's go see where the majority of cases are. And it's like, well, it turns out most people that lived here either went past this well on their way to work, to and from to work, or knew, their household got the water from that well. That well was the issue. So that's how you can, like, there's a correlation, and there's a story of, hey, I have a hypothesis of causation, I can test that before I do the correlation study, for example. Like, if this is true, this should be highly correlated, and they are. Hey, here's another one. So we talked about vaccines last week, right? We talked about, you had a great visual on pandemics, and there is a story like, well, if we have a pandemic stop or big diseases disappear because, well, sanitation improves. And in the case of cholera, yes, when you have central, water is coming out of a central processing plant, and all your sewage is completely separate and gets processed as well, cholera disappears. But you know how you also can get rid of disease? Immunize everyone against it, right? This is every state in the Union, and this is the number of cases of measles. So this has nothing, it isn't like we put central plumbing everywhere at this point. This is 1963, the measles vaccine is introduced, the numbers of death over time drops off. Doesn't matter where you are, there's several places in there that didn't have central heat, plumbing, or water at that point. That was still coming, but as soon as you add vaccines, it disappears. You can do this in Pakistan, where that's also still true. So it's the kind of thing where this is a good proof of correlation. Also a visual I quite like, except for the fact that you can't read that part as easily. So, use with caution, of course. Another huge study found no evidence that cell phones cause cancer. What's the WHO thinking? I think they got it backwards, huh? Well, take a look. You have total cancer incidence, it drops off, and then the cell phone users goes up. There's so many problems with that. To be safe, until I see more data, I'm going to assume all cancer causes cell phones, right? You can flip this. And so you need to actually go have an hypothesis before you do the test to go, A causes B. But it could be the other way around, or there might be a third cause altogether. So what is that number? There are several statistical tests to see if one quantity is related to another. There's the Spearman ranking, that's monotonic. There's the Pearson ranking, that's linear, and the Kendall-Tau, which is also monotonic. Monotonic means that it doesn't have to be linear. So it could be fast some time and slow other times. The Pearson ranking looks if A and B are linear correlated. Is there an actual line? The main difference between a linear correlation and nonlinear is but monotonic one. So Pearson, for example, I always have to look at it like that's the linear one. I confuse Spearman and Pearson, so see if you can catch me if I mess that up. So Pearson is the linear one, so if there's a linear correlation, this is a perfect linear correlation going down, so it's -1. And I have a perfect linear correlation going up. That's also +1. I have a correlation downwards, but there is some noise involved. So the correlation is between -1 and 0. And if it is correlation going up, but some noise involved, it's between 0 and +1, right? So noise is sort of correlated, like you get a positive value between 0 and 1 if it's actually linear, but a little noisy. So that's what you can expect from actual real data. These are edge cases. You don't get, usually we don't have data that's well behaved. Usually we have a little bit of noise in there. And if it's all over the place, we get a Pearson ranking of 0. So there is no linear correlation. So you can see how well the correlation happens, right? You actually have a measure of how good A and B are correlated. X and Y are correlated. Yeah? In a linear fashion. So with Spearman, it doesn't have to be linear. This would have a not so great Pearson ranking, but it has a good Spearman ranking because like it keeps going down by and large. It doesn't go down linearly, but it keeps going down or it keeps going up. So as long as it does that, you get very good Spearman rankings. So often I do a Spearman ranking and a Pearson ranking if I don't know if it's linear or not. When you go like, oh, it's monotonic, and I even get a better Pearson ranking, oh, then it's linear. So Spearman ranking, for example, is 1 here. Every next point for x is high. That means that the next point for y is higher. But the Pearson correlation isn't 1 because it's not linear. Yeah? All right. Then again, if this is sort of like, oh, you're welcome to your actual noisy data that we get in real physics, right? Like, welcome to real life. Like, this is what it actually looks like. Nobody gets this from a measurement, right? This is coming out of math. So now I have like a cloud of points, and they're both sort of like between 0 and 1. You're going to go like, I don't know. I mean, there's a cloud of points, and it sort of goes up. So it gives you an idea. It's like, well, this could be monotonic, this could be linear. It's not a great correlation. Yeah? Okay. Or you get something like this, which is like, yeah, I got most of my population doing a pretty linear correlation, like both of them are pretty good, except I have a few outliers here. Outliers can really mess this statistic up. Because if these are true, then it's sort of monotonic, and it's really a Spearman correlation. But if these are bogus, then this is a Pearson correlation that got messed up. So it's always important to visualize your data as well. But you have a metric, you have a number that you can report as well. So what you then need is a second part of the thing. Not only like how well they are correlated, but how much confidence do I have in this measurement, which is where the p-value comes in. So a Pearson or a Spearman ranking spits out 2 numbers. How much it is correlated, and how confident am I in this? So there is an XKCD for that, because there's always an XKCD for these things. So if you need to illustrate your stuff, jelly beans cause acne. Hypotheses. That's the thing. Whether that's true or not, let's scientists investigate. But we were playing Minecraft. This is our usual complaint. Fine. We found no correlation link between the jelly beans and acne. The probability p-value is greater than 0.5, right? So we had the p-value was too big, so you cannot reject the hypothesis that they were correlated. That settles that. I hear it's only a certain color that causes it. Scientist, but Minecraft. Okay, so we found no correlation between purple jelly beans and acne. P is greater than 0.5. Brown, pink, blue, teal, salmon, red, turquoise, magenta, yellow, gray, tan, cyan, green, ding, 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 ding. Suddenly P is smaller than 0.05, right? So we now have significance. But not for mauve, beige, lilac, black, peach, and orange. I don't actually buy jelly beans that much, but I don't know if there actually are 20 different colors and tastes, but flavors, but there you go. Green it is. Probably, right? So treated with caution, because then we reported like, well, we got a lower value, like we got a p-value smaller than 0.5. That means it is significant, right? And then I can report the news that green jelly beans cause acne. Except I did the experiment 20 times, and a 20th is 5%. And so if I do the experiment 20 times, there is always there should be one of them where the p-value is below, just by sheer random chance. Yes? No? All right. So treat with some caution. If you do p-tests, the p-value test. All right, that's on the recording now. Anyway, then you, especially if you don't have uncorrelated samples, then you are doing something called p-hacking. So why is everybody opposed to p-hacking? It's brilliant. Literally anything can be true. We control the economy. We can be telepathic. We can cure cancer. P-hacking makes you a wizard. If not for all the naysayers, we could wield total power over the entire universe. Are you sure that's true? Not yet, but if I can pick just the right data. P-hacking is when you, for example, say, oh, those must be wrong. No reason, but my correlation test is off, and so these points need to go. I don't check the points. I don't see if there's anything special between these points and those points. I'm just getting rid of them because they mess up my correlation statistics. This is malfeasance, right? And it's an easy thing to fall into because you can go like, well, obviously those are outliers. I should be getting rid of them. No, you should look at why they're standing over there. Is there a particular thing, like is there a particular third component? Like, actually, this is when the whole lab was at sweltering heat. We go like, okay, that's a fair reason to get rid of those points. Like something is off because, like if you find a reason why these are off and this is not the case here, then you can look at it and go like, this is a clean sample, this is spurious. But if you just go, well, that clearly, this means that these are just dumb, and get rid of them, that's called p-hacking. They are messing with my correlation statistics, and I really wanted a correlation statistic. That's the thing that you need to warn yourself for. Now, medical research and some other research has suffered from the fact that people did do p-hacking. And I think that's partly because we sort of put this hard line at 0.05. And that's because if below 0.05, you get to use the word significant. Significant is the magic word with like, look, we found something, you can build your policy, you can start investing based on this. Significant is where it gets important. However, you can totally have a p-value of 0.06 and go, you just don't use the word significant, but you go like, this is suggestive, this is something that we need further study. Like, I think that's perfectly fine. Not making it that hard, that hopefully takes out the onus that people won't go like, oh, I'll just start, like I'll fudge the data, because there's now no extra pressure on people to do that. So for example, here you have one of my favorite artificial data sets, which is the Anacomb data set. It is the one that had the same statistics for the X and Y values. And they have the same, look at the Spearman, Kendall, Pearson rankings. They are all, but they are different, right? Because here, like, this is linear. This is quite linear with an exception. So let's look at which one was the linear one again? Pearson, let's go back. Bleep, 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 bleep. Pearson ranking is the linear one. So which one of them is linear? This one's pretty linear. Look, it has a 0.82 for the Pearson, 0.82 for the Pearson. Yep. So that could be noise in all the points or noise in one point. 0.82 for the Pearson. This is not terribly linear. So this is where you go for like, hey, the Spearman ranking is much lower. And that's because it goes back down. It's not monotonic, right? Pearson is just going, how linear are you? And you're allowed to go back down. So it looks for a slightly different thing. And here it goes like, well, these are all still good, although Spearman and Kendall are both lower. It's because everything is driven by this one outlier. But what I put in behind it is the actual p-values. P-values here are 0. They're very, very low. They're much lower than 0.5, like it's 1% here. 0 here. Yes, these are definitely, it's monotonic, it's linear, monotonic, it's linear, yep. Here, I'm still pretty confident, so hey, it's not actually perfect, but I want to notice that if it's like the majority it's all hanging off one outlier, then actually our p-values give us a reason to pause. So these are not perfect tools. So the reason that I'm showing it to you like this is that, hey, I got a visual and a statistical test. I'm showing you both, right? So if you do a scientific result and go like, hey, there's a really high correlation, if you're got a good referee, they go like, cool, show me the data. Like, this is the show me the money version of science, right? Show me the data. But if you go, there's a high correlation between these 2 points, and you just visualize it, you go like, how high? How good? Give me the statistical test as well. So if you do both, you go like, look, this is all we got, all the cards on the table. There is the correlation. This is what it looks like. Because you base your entire rest of your argument off this. This is how good it's correlated. Therefore, A causes B, or the A is correlated with B, because that's what I really know, and therefore, right? That's the next part. So, second part, are these cases from the same population? And this is critical if you do a observational kind of science. I do an observational kind of science. You cannot change the universe because it's just sitting there. I can't reach out and go like, move that star a little bit over, or let's change the perspective on this galaxy. So I need to know if population A and population B come from the same parent population. So I already said, what happens if I go to St. Matthews versus the West End and do a survey? That could be any, like survey statistics. This is really important because then you can ask things like, what's your annual income? And if population A has an average annual income of like $80,000 and population B it's like $60,000, all the rest of the stuff that I'm asking them is probably correlated with that. And so you want to know if the sample from A and the sample from B are the same. And so Kolmogorov-Smirnov test and the Anderson-Darling test are the two that you use here. Two samples against each other, that's what I just gave as an example, like group A, group B. I can do this with heights, for example, like 6th grade versus 8th grade. I got my two samples, I got a bunch of heights. You're going to have two different samples. They're different. They're noticeably different. Meanwhile, you can have an 8th grader that's the size of a 6th grader. One doesn't work. It's a statistical thing, right? The whole group is taller as a whole. Maybe even the mean won't show that, but the whole group you can compare. Test the sample against the fiducial distribution. Let's say, hey, height should be a Gaussian. Here's a Gaussian that I'm expecting, or this is what's coming out of the CDC for 8th graders, and now I can compare my class to it. Oh my God, my entire class is 2 inches too short, right, on average. Like, it's completely off. Well, that's because there's one kid that's huge, and then everybody else is sort of fine. Right? You can look at those things. So sample versus sample. You look at two samples, and you want to know if they're actually the same. Okay. It always looks good on my screen, and then I keep forgetting that it doesn't. Percentage of the world population living in the next year. So basically, you go the time, the time line, and as you go along, you have a bigger the population that actually now lives in the next year. So you can do that, like what fraction of the sample do you have below a particular value? So if X goes or below. Does this make sense? This is called a cumulative histogram. Has anyone encountered cumulative histograms before? They're kind of peculiar.
I've seen them.
Okay, so yeah, cumulative histograms are useful if you are trying to compare two completely different distributions. So if you have a Gaussian and you have a log normal, for example, you're like, how much of the how much of the sample do I have when I get to this value? Like, that's what you're basically plotting here. So let's say I've got a mathematical distribution, or essentially a sample of infinite size. So that's a smooth curve. But meanwhile, I have a much smaller sample of discrete values. Those are actual observations. And that's when you start looking like a little sawtooth diagram, because like every time you get one value, you sort of jump up a big chunk of the fraction. Does this make sense? All right, so the neat thing is you can compare an almost infinite sample to a small sample. So I can compare a small new study to the giant study I already had and see how well they agree. So completely different sample sizes is a hard thing to compare, because if I want to say, let's see, I do a study here in Kentucky. Even if I get every Kentuckian in the state, I have a sample of 2 million people. I want to compare that to the WHO study, which has 1 billion people in it, right? This is a huge discrepancy in, like, I have big numbers, but there's a big difference in the sample size. If I wanted to see if the same conclusion holds, I want to check if, let's say, like some sort of metric holds, height, BMI, some sort of like single number metric, if it holds across both samples. So I can have like, here's the billion number study, and here's like the Kentucky study, and I can see if they compare okay. Yeah? All right, so what does the KS test actually do? So really disparate sizes are allowed, so that's a really big benefit. I look for the biggest space between both distributions. That's it. Where do I see the most daylight? It's like this arrow here, this is the biggest gap between the blue sample and the red sample. So if the blue and the red sample are identical, they basically go through each other. They sort of like circle each other, but here's a gap. So, okay, that's the biggest gap I can have. So the biggest it can be is literally 1. So the KS maximum value is 1. Smallest sample is effectively 0 when they follow each other. Okay. So look at either a mathematical distribution and my data, or data sample versus, and those two don't need to be the same, roughly the same size. For a lot of statistical tests, it's like, look, both of the the test samples that go in have to be about the same size. I mean, it could be like 150 versus 200, but not, 5 versus 20 million. And with the KS test, it's like, yeah, you're still fine with 5 versus 2 million. I mean, there's always a point that it sort of breaks. I mean, you probably should get more than 5. But at any rate, you can compare 2 samples, and even a small sample versus a big sample. I find this a really useful property. So everyone likes this one, or at least the astronomers love the Kolmogorov-Smirnov test, because they basically have all these different samples. And so it's a distribution. We don't care about the distribution. We don't care if it's Gaussian or log normal or whatever. So it's completely agnostic on that part. It's universally applied. Like, a lot of people know what the KS test is, even if they don't know what it stands for. It has critical values. So essentially, value that comes out as well immediately tells you if it's a random happenstance, or it thinks it's a happenstance, if it's significant or not. So you can do it even as a goodness of fit test, and it's easy to compute and familiar to all astronomers, physicists. And so it's an easy thing that you can get, right? However, as Yoda says, there's always another one. And so that is called the Anderson-Darling test. There are some dangers to the KS test. And if you befriend a mathematician, especially somebody who is a statistician, they will tell you that the KS test has some sensitivity issues, right? So it's not so sensitive to the wings of any distribution. It's really sensitive to where the bulk of your data sits. Now, that can be just perfectly fine, but if you have, for example, well, like, yeah, I have something that a lot of wings are in there. So an alternate is the Anderson-Darling test. It doesn't get normalized, so it's not a value between 0 and 1. It's literally a random value, and it then gives you where the significant levels are. So it's a little harder to read. But other than that, it's a second test where you can do the same thing. So especially when you get a KS test and you have a p-value that's like 0.49, you go like, okay, we're dangerously close to 0.5. So let's have a look. Let's check with the Anderson-Darling test if it agrees with it. But the critical value is like, it tells you how much gap there is. So the critical value essentially says this is the measure of gappiness. This is how much the two distributions disagree. And then the p-value of how good that value is, like how confident it is in that. So if you have really small samples, the odds are that it will give a p-value that's above 0.05. It just goes like, yeah, they're this far apart, but that could just be a random happenstance. So we have 3 tools here now, although I only gave, like, this is 2 together. The first one is, how much does A know about B? How much do they correlate? The second part is, so if I make A bigger, does B grow as well? Is that linear? Or is that monotonic, right? It keeps going up, but it's not equal amounts depending on the value of A. The second part is, hey, I got sample A, I got sample B. how much are they alike in this particular property? So you can say, hey, how many thought experiment. 6th graders, we do height distribution. The height distribution for class A and class B is the same. Okay, so whatever happened, like we at least fed them roughly equally, so they all are basically the same height. Like the distributions agree. The KS test, this has shrunk to small enough and the p-value is small enough that we're like, yep, it's significant. So then we can say, like, well, assuming that height is all I need to know about a 6th grader, we can now look at their test scores, for example, because these are equal groups of 6th graders. Did I use the right metric for that? Probably not. Right. There's a fantastic study where they go like, oh, kids' test scores are better they took the number of books in the household. And then they went, oh, the more books you have in your house as a kid, the higher the test score. So there was some fantastic logical error there, because they kind of go like, these 6th graders must be grabbing, the dad's books off the shelves and reading them and getting better test scores as a result. No, this was a common thing, right? If you have more books in the house, it means that the household probably has a higher income, because books are expensive and they are, in effect, a luxury item. And two, education, or at least information, is valued. So those are two things that are root causes, and the books are sort of a proxy for that. So you could say, like, well, what I should do is household income, for example. And if class A and class B has the same household income, and then they're in different schools, then look at the test scores, right? So you use this KS test to make sure that you've got the same root group, for example. They come out of they're similar enough in otherwise circumstances. Okay, you can get really depressed about, test scores and root causes and all that good stuff, but it is important to remember that you test against the right things. And then you can say, like, well, are they Gaussian, or is there just one hyperactive kid that up to college and that he's just sort of pulled one way? And so you can say, like, well, is the distribution of test scores, for example, Gaussian? It should be 2 first-order Gaussian. And so you can compare that. Oh, look, class B has one little genus in there, and that sort of pulled everything up off the edge. So here's our every week I'm trying to give you another hammer in your toolkit. This is another hammer. If you have samples, you can now say if A and B are correlated. You can say if sample A and sample 2 are actually from the current distribution or not, and if you can therefore compare them. And the other one is like, hey, are they normalized? Do they adhere to a particular distribution? This is almost everything you need to do in order to do a scientific study. Really. I mean, a lot of my undergrads have done a whole paper where they just report KS values and go, these two distributions are the same. If I separate out by this one, and this one are the same, but those two are not, for example. That's a valid result because you did a statistical test, you did the visualization, and you have a p-value. You can say, like, it's this likely. Okay, any questions about statistical testing? I know, Monday morning, and I just flung like half a toolbox at you in Python, but yeah, this is the useful bits. All right, what we're doing next week is called bootstrapping. Bootstrapping and jackknifing. If I don't know what my uncertainties are, how in my inferred values can I get one? Because a lot of the time, you just don't. Okay, who knows the story about Baron von Munchausen? I always get like a phenomenal number of blank looks when I say that, right? This is a 19th century tall tales series, right? So this is the Grimm fairy tales. So this was sort of like a series of stories about a fictional baron in Vienna. And one of them is he pulled himself up by his own bootstraps. Now, I'm willing to bet that all of you have heard that expression. Yeah? You know, why don't these people pull themselves up by their own bootstraps? And I find it incredibly funny because anytime anybody says that with a straight face, they actually mean that people should pull themselves up by their own bootstraps. Clearly, they haven't either done the experiment or B, know the history of the expression. The expression is that Baron von Munchausen was riding along, and he and his horse both basically fell into a swamp, and they were sinking. And he was like, well, how did you get out of that? Well, I grabbed my own bootstraps, or stirrups, I think, and just pulled myself out, which is literally something you can't do unless the horse sank and you got out, right? So it's something you can't do, but bootstrapping comes out like, well, I don't have any other solution out of this. I can bootstrap my way out. I can sort of pull, like what he did was like, I pull one boot out, and then I pulled another boot out, and sort of like, well, what were you standing on, right? Nothing. It was like, okay. Google Baron Munchausen bootstrapping. This is where the phrase bootstrapping comes from. We'll get into that next Monday. We will be doing fitting and correlation functions this week, and then next week we'll actually go like, okay, we were doing fits, and we were doing fits with uncertainties, and we were doing statistical tests, and we're getting p-values, but what do I do if I don't quite trust the uncertainties? This is one of the tricks. Okay? All right. That gives me 2 minutes to spare for anybody who has a question. I will be putting in the midterm grades. That's not quite, I'm not quite there yet. I'm also doing that for the next other class I'm teaching. But hey, congrats, because I definitely know that everybody passed. Like, this was a good, everybody, well done on the talks. I really enjoyed them. I really enjoy seeing what you're interested in. So good job. We keep going with the assignments, and that's majority of the grade. We do have a final, but you know, you keep doing the assignments and you'll get there. Okay. I will see you on Wednesday when we work on assignments 7 and 8. Yeah?